So my name is Pascal. I'm not an expert in machine learning or deep learning or anything like that. I come from the, I would say, cryptography community. I've been working all my life pretty much on homomorphic encryption. I fully realize that you guys in the audience may not be familiar with what homomorphic encryption is. So this talk is, destined to be very, very high level and very clear. And I'm not going to dig into details or anything like that. I think the most important thing for me today is to explain a little bit what is coming in the machine learning arena, I would say, and the problem that it faces currently with accessing sensitive data, which is a big problem for which we actually have a solution. So with that, so obviously if you run some kind of machine learning service, let's say in the cloud, you have at some point to collect the inputs and data that is coming from your users. And so, all the algorithms are processing personal data in a way or another. So there is a dedicated name for personal data, which is PI, say the normative and regulatory communities. And of course, it's a big thing today because accessing to personal data is kind of preventing from the generalized adoption of machine learning. It's really a problem that is becoming more and more important. And so we can't really benefit from the advantages of machine learning because of this problem of accessing personal data, which is governed by data protection laws and the like. And so the elephant in the room, if we look at, I would say, a typical application of machine learning. So assume that some company, some cloud service operator, Mr. Cloud Inc., has collected a huge amount of data, has used these data to train some kind of cognitive model, typically a neural network, and is running an inference service in the cloud, possibly based on GPUs and the like. So Mr. Cloud Inc. actually exposes some kind of an API to its customers. So the customers basically will send data, and the inference will be processed in the cloud, and then the prediction or classification or whatever the result of the inference would be given back to the user. So the problem that we have here is that the inputs themselves can actually be sensitive. So there are so many examples of that. So the problem that we're facing here is not that it's sensitive towards outsiders. You can always use HTTPS or some kind of encryption for data in transit between the user and the cloud operator, but it doesn't solve the problem that the operator itself can actually see the data. And moreover, the result itself of the inference can be sensitive as well, because you're extracting information out of the input that is given. So think of all the contexts in which this is not acceptable. So if we think of the future of genomics, for instance, it's easily understood, and people have, very quickly this feeling that they would not agree with sending their genetic information to some operator in the cloud so that we can detect genetic diseases or defects or even just genetic threats, because then the operator has access to the data. It's exactly the same for your health status, your lifestyle tracking, and all the devices that we use every day, to monitor how fit we are and how we exercise and everything. So if at some point all this data is being collected in the cloud and processed there, of course it's beneficial to you, but there is a problem with accessing this data. Same thing with a lot of other applications, typical applications of machine learning. You can think of the financial sector, where you actually have to process portfolio information about your positions on the market, and these could be confidential. So there are so many examples where it's actually not acceptable to send this data, and so the big problem with machine learning is that in this context, in this particular setting, the service, the machine learning service, actually not only processes personal or sensitive data, but it exposes it. And this is where homomorphic encryption comes into play. So homomorphic encryption is, I would say, a kind of encryption that is that looks like magic. It actually allows you to process over encrypted data without having to decrypt them. So it means that as a user, I can actually encrypt my sensitive data using a key that I'm generating for myself. So I'm the only one with the encryption/decryption key. It's private, it's secret. I keep it somewhere securely, maybe in an embedded device, or whatever, in a secure place. And then whenever I have to send some inputs to the model for the inference to be run in the cloud, what I'm going to do is just encrypt my data, send that encrypted, push that encrypted to the cloud, and then all the inference, the evaluation of the neural network will be done in the encrypted domain. That is, if you look at information, so you have the plain text domain where you do everything in the clear. So you compute everything in the clear, and you have like the encrypted domain where, thanks to homomorphic encryption, we can kind of simulate or replicate any kind of computations over encrypted data. So you take as input encrypted data, you never decrypt them, you just process them encrypted, and you get you carry out the computation, the homomorphic computation, and you get an encrypted result. And so you can, by just combining several homomorphic operations, you end up with some kind of a homomorphic equivalent of the original algorithm. But the big advantage is that the person or entity that you have delegated the computation to actually does not see anything. It's just encrypted stuff. And there is no way you can actually break the encryption. We can guarantee a certain level of security. So with that in mind, we can directly think of applying homomorphic encryption to this setting where there is some kind of a crypto front end for users, and they just encrypt and decrypt the results that they get. And so in that case, it's kind of a paradigm shift, because we're now protecting user data and separating very clearly, putting a separation between data coming from the user and information about the model, which is kept in the cloud. So we think it's a revolutionary, a new way of doing machine learning. So it means machine learning in the future will be able to actually preserve the privacy of data. And this is exactly what we do at Zama. So at Zama, what we're doing is building the first ever suite of open source tools that allow like anyone to benefit from homomorphic encryption. And so we're building like a set of tools, thanks to which you can just push the button and go from having an inference service in the cloud that does things naively, I mean, on plain text data, and convert that automatically into an equivalent service that does that on encrypted data. And so I should say a few words about homomorphic encryption, and because this looks like magic, a lot of people can actually be very, very skeptical about the existence of homomorphic encryption. So the first time homomorphic encryption was discussed was like in the 70s. Like it's a dream of cryptographers. It has been for a very, very long time, but it wasn't until 2009 that the first example of an implementation was actually shown to exist, and it was a very big eye opener for the cryptographic community. And then since there have been a lot of research and a lot of evolution, and performances have increased, and so on. So if you want just to look at the paradigm of homomorphic encryption, it's very easy. So the same way there is symmetric encryption and asymmetric encryption, where you have a public key instead of a secret key to encrypt things. We have the same notions in homomorphic encryption. So basically the user would be on the left, and the cloud operator, typically the entity to whom you're delegating your computations, is on the right. And so you're just generating the red secret key there would encrypt your data. You would send the encrypted data to the entity that processes it. And then you can apply any kind of function to the encrypted, to X in encrypted form. You just have to give also a public key that matches your secret key. But this public key does not reveal anything about the secret key. And so at the end of this computation, the entity ends up having an encrypted version of f of x. So you have applied f over the data x. And then this encrypted value is just sent back to the user, who can decrypt it using the secret key. So it's a bit confusing because it's symmetric FHE, FHE standing for fully homomorphic encryption, but there is a secret key and a public key. So it might be a bit confusing for people who are unfamiliar with FHE. And at the same time, there is asymmetric FHE, which means that you can actually give an encryption public key to other people. So other people can actually use your public key to encrypt data that they generate and push that themselves to the entity that processes this data homomorphically. The entity applies the same circuit given the evaluation public key, which is different from the encryption public key, and then end up with this encrypted result, which is sent to you, and then you can decrypt the result of that. So amusingly enough, well, interestingly enough, it's these two settings are actually equivalent, which is a big thing, because generally in encryption, there is symmetric encryption, which has its own realm, and then public encryption, and these are like two separate domains, even in terms of expertise. But here, because it's homomorphic encryption, we can actually convert one into the other. So that shows how profound homomorphic encryption is and how different it is to classical encryption. And the first example was actually discovered by Craig Gentry. So he was with IBM at the time, and he showed an example by which you can actually encrypt bits. So inputs, data are just individual bits. So you're just splitting everything into bits, and you just encrypt them separately. And so he showed the first example ever where you can have an encryption of 2 bits, say X and Y, and then compute the encryption of the XOR of these 2 bits, their addition mod 1, mod 2. And then you can also do the same thing for the multiplication mod 2, which is the logical end. The big problem he had when he did that, it was the addition, the XOR was pretty reasonable in terms of time. But the multiplication was like super slow. And so it wasn't, I mean, the goal of this work was not to make FHE efficient, it was to show its existence. And then if you want to dig into the details there, actually there is some kind of a notion of noise attached to ciphertexts, to encryptions of bits. So you have to put some kind of random values in there to protect what we call the semantic security, but I'm not going to dig into the details there. But there is this notion of noise, which is incorporated, embedded into the ciphertext. And every time you do a homomorphic operation, the noises coming from the 2 inputs are going to merge somehow. When you do an addition of 2 bits, the resulting noise will be approximately the same as the input noises. But when you do the product, when you do a logical end, then the noise kind of doubled in Gentry's implementation, doubled in size. So meaning that if you do like a few multiplications in a row, then every time the noise will double in size. So you get something that is exponential. And so after some point, the noise becomes so big, you you have done your homomorphic operations, but the noise now it's so big that it actually overflows onto the plain text, and you're losing the consistency of your data, meaning that the ciphertexts are not decryptable anymore. During this work, actually, Gentry came up with the idea of bootstrapping, which is this kind of magical operation by which you can actually apply the decryption circuit homomorphically and kind of reset the noise. So you give a noisy ciphertext of some data, you just apply bootstrapping to this data, and you end up with a ciphertext of the same data. So the encrypted data hasn't changed, but the level of noise is now reset to its nominal value. And so you can go on with computations. And so with the bootstrapping, at some point you can go on with computations, and you can, in theory, virtually do a limited number of operations. The problem was the bootstrapping was excruciatingly slow. So it wasn't until actually 2012 and further works and further discoveries that the bootstrapping operation could be improved, but it always remained very slow, like the limiting operation in FHE schemes and crypto systems. But since 2009, a lot of things have been done. A lot of improvements have appeared in the literature. A lot of people have taken a sudden interest in fully homomorphic encryption, and given the huge number of applications. And you can find a lot of open source libraries on GitHub and on the web that implement actually various schemes and variants. And so there are several ways of doing homomorphic encryption, and so there is some kind of diversity in there. But what is very interesting for us at Zama was that about 4 years ago was invented a new way of doing FHE, which is called Torus FHE, FHE on the Torus, or TFHE. And the very interesting characteristic of this fully homomorphic encryption technique was that the bootstrapping is particularly fast. So it just takes a few milliseconds, maybe a few tens of milliseconds to actually perform the bootstrapping. So you take an encryption of X, which has a big variance, meaning a lot of noise in there. You apply the bootstrapping, you end up with this equivalent ciphertext with reduced noise, and then you can go on with your computations. But now it doesn't take like years to do the bootstrapping. It's just, it takes a few milliseconds. So it's kind of it was kind of a new opening for the research in that area. And what we did at Zama is actually to extend this bootstrapping to make it programmable, meaning that at the same time that you're resetting the noise in an encryption, you can actually put in there as a auxiliary input a function of your choosing. And when you do that, you end up at the end with a low noise ciphertext, but the function has been applied on the plain text. And it can be like a nonlinear, quite complex function. And in addition to that, the variables, instead of being on bits, can actually be reals. And at the same time, you have a lot of SIMD features, which actually make all the computation parallelizable. So it was applying, using programmable bootstrapping, you can actually use that to simulate artificial neurons. And the way you do that is that, so if you look at a neuron, it's just composed of these two parts. So you have the scalar multiplication, actually of the vector of inputs with the weight vector, and you add a bias. So this is just an affine computation, but this is fine. Any FHE scheme is very happy with linear or affine computation. So it would be quite efficient doing that. The big problem that cryptographers faced with trying to apply homomorphic encryption to neural networks was the nonlinear function, the activation function, which is precisely made to be nonlinear. It's important that it's nonlinear. And when you want to do that, it means because of the nonlinearity, you have to compose operations to simulate simulate this function in the encrypted domain. So what people have been doing, people using like, I would say slow bootstrapping schemes, have been stuck because of that. So they kind of approximate the activation function with some kind of polynomial. But then it means because they never bootstrap, at some point they run out of noise budget. So the noise becomes too big. And so if they want to go through all the layers in the neural network, they have to provision a huge noise budget right from the beginning. And it makes like the homomorphic evaluation completely unrealistic. Using programmable bootstrapping, we can actually bootstrap, apply the activation function, the exact true activation function, not an approximation, to the multisum, and so we can actually simulate quite very rapidly a neuron. And if you take my word for it, we actually have other improvements, other tricks that allow us to support not only neurons, but any kind of computational ingredient of neural networks. So batch normalization, regularizations, max pooling, softmax, convolutions, of course, any kind of layers that you can find in ML frameworks, we can actually support in the encrypted domain. And so because of that, it gives us like a paradigm shift. Now we can actually take as input like a pre-trained neural network that was trained separately by somebody, take just the representation of this network, and for instance in ONNX format, and then convert that into some kind of a homomorphic equivalent. And the resulting performances for the homomorphic inference in the cloud is like the fastest you can find. So there are still a number of challenges, of course, specialized hardware, maybe GPUs, FPGAs, ASICs to boost performances in a way or another. And a lot of people are actually very interested in doing the training homomorphically. We don't have a solution for that yet. We're working on this, but it's on on our research list of topics. But so far, we're not supporting training, homomorphic training, just homomorphic inference. So the big advantages, again, is that if you compare to previous approaches like CryptoNets, so it was basically applying homomorphic encryption without bootstrapping and provisioning that noise budget and everything, it's considerably more efficient, and it scales linearly. I mean, the performance of the inference is linear in the number of neurons, so it's independent of the number of levels. So it means we can address deep models, like any number of layers. And so we end up with a high throughput engine for inference. So we're in the process of building a technology stack. What we want to do is to provide to developers or anyone who's interested in this technology to be able to use it without any prerequisites whatsoever in cryptography. We know cryptography is very, very delicate. It's very easy to screw up with it. It's very easy to misuse it, to use bad parameters, and so on and so forth. So that's why what we're doing is going to be open source from A to Z. And in particular, what we're building right now, so there are several things that we're building in the tool chain, but the big ingredient is an SDK, a library. We use Rust for that, for consistency and for liability. It's a kind of a library that executes like all the FHE operators. And then what we're going to provide is bindings like wrappers that allow you, whatever your preferred programming language is, to access this library so that you can actually program your own homomorphic operations. And so this comprehensive library is meant to be optimized and adapted to the hardware that you're using. So, of course, the first target is CPUs, multi-threaded CPUs. But GPUs are also of high interest because we can parallelize everything. And we can also think in the future of having like a hardware accelerator to boost performances even more. So there is the SDK that is going to be released, the first version, theoretically in September. And also what we're working on is a homomorphic compiler. So the homomorphic compiler is going to take care of all the cryptographic details, which are not details, they're like super important if you want to achieve any level of security. But it should be usable in a very, very user-friendly way, so that even if you don't have all the crypto expertise, you can just push the button and it will convert your neural network into a homomorphic equivalent. And then once you've done that, all the parameters and the homomorphic conversion has been done and optimized, and then you can just take your inference engine, your execution engine for your model in the cloud. You just unplug this, you plug the new converted model, and then you're good to go. The only addition that you have to put into your game is you need to provide your clients with some kind of a crypto front end, because now they need to encrypt inputs on the fly when they're going to call your service, and then to decrypt the result that you're processing. But it's very easy in principle to like convert and benefit from having this layer of homomorphic encryption on top of your machine learning service. That's basically it. I tried to make it short because I was like sure that there would be like a lot of questions. So I'm kind of done and ready to answer any of your questions.
Amazing, thanks, Pascal.